Assalamualaikum everyone. We are from Group A. Today we will present brand study for our gas processing. This is our group members, which is consists of me, Siti Nazira, Muhammad Asnur, Izu Afiq Shah, Danny Alistair, and Muhammad Azhar. Moving on to the next slide. This is the content for our presentation, which is firstly introduction, second methodology, third modeling, fourth results and discussion, fifth proposed action plan, and lastly conclusion. Okay, next I will pass to the next person.
Assalamu alaikum. My name is Muhammad Azhar bin Muhammad Izzuddin, and I will present the introduction and the conclusion. So, for the background of natural gas processing plants are responsible for converting raw natural gas into pipeline quality gas suitable for industrial and domestic use. However, raw natural gas contains several impurities such as hydrogen sulfide, carbon dioxide, water vapor, and heavy hydrocarbons. These impurities must be removed through multiple processing stages, including separation, compression, acid gas removal, dehydration, and natural gas liquids recovery. But because these processes are highly integrated and interdependent, the system is very sensitive to failures. Any failure in critical equipment can significantly affect plant performance, compromise safety, and disrupt production continuity. Next, for project overview and analysis approach, in this project, a reliability, availability, and maintainability, or RAM as you can call it, study is conducted based on a reliability block diagram model. The plant processes two gas streams, a medium pressure stream and a high pressure stream, each contributing 50 mmSCF per day, resulting in a total output of 100 mmSCF per day. The system includes different configurations such as series systems, parallel redundancy, and standby units, which all influence the overall system reliability and availability. To evaluate the system performance, failure and repair data were analyzed using Weibull++ and BlockSim. Live data analysis and repairable data analysis techniques were applied to assess the plant's performance over a 5-year operational period.
Moving into our technical methodology, we utilize two primary software environments for this run study, which is Weibo++ and BlockSim. Our process begins with live data analysis or LDA. We imported historical failure data into Weibo++ to identify the best fit distribution for each equipment group. Using the likelihood value and AIC as our primary ranking criteria, the shape parameter or beta was crucial here. It told us whether a component was in its infant mortality phase or failing randomly or entering a wear out stage. Parallel to this, we perform repairable data analysis using the power law model. This allowed us to track performance trends over time. If we saw a beta less than 1, it indicated reliability growth, which meaning the system is improving. Conversely, a beta greater than 1 warned us of reliability degradation. Finally, these failure and repair distributions were integrated into BlockSim. We constructed a reliability block diagram, which is RPD, using series and parallel configurations to simulate 5 years of plant operation through Monte Carlo simulation. This gave us our final averages for availability and downtime. Moving on to the next slide, which is modeling assumptions. To ensure our simulation was both mathematically sound and focused on the most impactful data, we established several key modeling assumptions. First, regarding system scope, our model focuses strictly on major process units. Auxiliary systems were treated as non-failing blocks to prevent minor peripheral issues from skewing the high-level plant availability results. We also assume a continuous steady-state operation over the 5-year study period, which is meaning no planned turnarounds were included in this specific model. Crucially, for our maintenance logic, we applied the expect as all repair assumption. This is called a conservative and realistic approach where a repaired component does not return to as new condition, but instead retain its accumulated degradation. We also assume unconstrained resources, which meaning repairs begin immediately without waiting for spare parts or labor. Lastly, all failures were treated as independent events, which allowing us to isolate the specific factors that are truly driving plant downtime. Next, we move to the next slide.
For live data analysis, we summarize the reliability parameters of the plant's most critical assets based on their operational impact and data significance. From the results, compressors follow a log normal distribution indicating complex failure modes typical of rotating equipment. Aftercoolers and reboilers follow a Weibull distribution with beta values greater than 1, which means they are in the wear-out phase and their failure rate increases over time. In contrast, pumps and motors follow an exponential distribution with beta equal to 1, indicating constant random failures. However, pumps have the lowest mean time to failure at about 0.63 days, making them the most frequently failing components. Overall, This analysis shows that different equipment exhibits distinct failure behaviors, with rotating equipment being particularly critical. For repairable data analysis, we evaluated the performance trends of key systems using the beta parameter and failure intensity. The results show that most equipment is deteriorating over time, as indicated by beta values greater than 1. Trim coolers have the highest beta at 1.78, making them the worst performer with rapidly increasing failure frequency. Suction drums also show rapid deterioration and pose a high risk of process interruption. Reflux drums and the slug catcher are similarly degrading, indicating aging equipment. Pumps also show a deterioration trend, confirming fatigue behavior in rotating equipments. Overall, the RDA results indicate that the majority of equipment is experiencing wear out, which increases the likelihood of failures over time. For the system-level analysis, a reliability block diagram was developed using BlockSim to represent the plant's functional dependencies and redundancy. Major process units were modeled as blocks, while auxiliary systems were excluded to focus on key contributors to availability. The system was configured using series, parallel, and standby arrangements, where series components require full operation and parallel or standby components provide redundancy. Logical nodes were used to represent process flow interactions. Monte Carlo simulation was then performed over 5 years using the failure and repair data from LDA and RDA. The model assumes an as bad as old repair condition, meaning components do not improve after repair. The simulation outputs include availability, reliability, and downtime, allowing us to identify critical components and system bottlenecks that impact overall plant performance.
Hello, my name is Nini Alistair, and now we are moving on into our results. So this section shows the baseline performance of the plant over a 5-year mission, totaling of 43,800 hours. And using the simulation in BlockSim, we've also determined that the current average plant availability is only 52.51%. This is a very critical finding as it falls nearly 47% short of our industrial target of 99% availability. And the primary driver behind this low figure is an astronomical system-wide MTTR of 20,802.37 hours. So this indicates that under the current condition, the plant is crippled by extreme logistics delays and also the lack of spare parts, where a single failure can also lead to years of cumulative downtime. Furthermore, the plant is predominantly a series configured system. The overall reliability effectively drops to 0% early in the operating cycle. To simply put this, our current reactive maintenance strategy with zero preventive maintenance hours makes a total plant shutdown a statistical certainty. And this is the table that shows the values mentioned. Moving on to the next section. So in this section, we move from the system level to identify the specific bad actors causing this disruption. And our data points that the reflux pumps and lean amine pumps as the bottlenecks in the facility. These pumps hold a failure criticality index of around 0.1699 and have accumulated over 6,500 hours of individual downtime. And when we look at our live data analysis, pumps and motors stands out with the highest failure frequencies, showing the mean time to failure of less than 1 day. This high frequency is compounded by deteriorating reliability trends. Specifically, our repairable data analysis RDA results shows that the trim coolers and the suction drums are rapidly deteriorating, with beta values of 1.77 and 1.75 respectively. And this means that the failure intensity is actually accelerating as the plant ages. Lastly, the sweet gas cooler and the trim cooler each contribute approximately around 2,000 hours of downtime because these are static assets sitting directly in the serial process line without bypasses, and their inherent reliability is major limiting factor for the entire plant.
Hi and Assalamualaikum. My name is Izu Afisha, and now I'm gonna be presenting about the proposed action plans. So we have four proposed action plans. For the first one is the implementation of redundancy for high criticality assets. N+1 redundancy should be implemented for the reflux pumps and lean amine pumps. This is so that the system operations are maintained during repairs through the addition of a standby pump, which effectively masks the 6.549 kilo-hours of downtime observed in the current serial configuration. Second is the MTTR reduction and spare parts or optimization. A critical spare inventory and service level agreements with vendors should be established to cap repair times at 48 to 70 hours. Logistic lead time is significantly reduced, thereby lowering the long hour mean time to repair that currently impacts system availability. The third one is the transition to proactive maintenance. Preventive maintenance cycles should be introduced for all rotating equipment, including motors and compressors. Predictive maintenance, such as vibration analysis, should be implemented for the expander compressor and residual gas compressor. So that the long duration corrective maintenance downtime is replaced with shorter planned outages by addressing potential failures before they occur. And lastly is the material and design upgrades for asset integrity. A root cause analysis, RCA, should be performed to determine if failures in the sweet gas cooler and trim cooler are caused by corrosion or fouling. Metallurgy should be upgraded based on the RCA findings. The justification of this is that the frequency of failure events is reduced by improving the inherent reliability of these static assets, which is critical given their high failure criticality index.
In conclusion, our RAM study has provided a comprehensive evaluation of the plant's performance based on the RBD model and 5 years of operational data. From the live data analysis, most equipment follows an exponential distribution with a beta value of 1, indicating that failures occur randomly and are not age dependent. However, certain components such as discharge and suction drums exhibit more complex failure behavior. From the repairable data analysis, some equipment groups show deteriorating performance with increasing failure rates over time, while others demonstrate reliability improvement, likely due to effective maintenance practices. Despite these improvements, the presence of deteriorating components within a predominantly series configured system significantly reduces overall plant availability. Equipment with both high failure rates and longer repair times were identified as critical bad actors. To address this, several strategies were proposed, including implementing redundancy, reducing repair time, adopting predictive maintenance, and upgrading materials or design. These are essential to achieve the target availability of 99%. Overall, our study highlights the importance of RAM analysis in improving operational efficiency, ensuring safety, and supporting long-term sustainability. That concludes our project. Thank you for listening.